Welcome to The Explainer. I am absolutely thrilled to take you on a journey today into a literal cornerstone of modern theoretical physics. We're diving straight into the legendary 1984 paper by Belevin, Polyakov, and Zamala-Shishkov, which, let's be real, most physicists just affectionately called a BPZ paper. Today, we're going to completely demystify its brilliant, honestly mind-bending math and see exactly how it fundamentally reshaped our entire understanding of the quantum world. So, right off the bat, I want to hit you with a bit of a weird question. What do boiling liquids and the fundamental strings of our universe have in common? I know, right? It totally sounds like the setup to a nerdy physics joke. But as you'll see from the source material today, the answer is no joke at all. It actually lies in this profound, seemingly abstract mathematical quirk that was discovered to exist in exactly 2 dimensions. Here's our roadmap for the explainer. We're going to cover the power of conformal symmetry, the magic of 2 dimensions, the stress-energy tensor engine, families of quantum fields, and finally, strings and phase transitions. Section 1. The power of conformal symmetry. Okay, so what even is conformal symmetry? Well, directly from the source, it's defined as a transformation where the interaction of fields at a critical point is invariant with respect to scale transformations. Basically, it preserves angles, while the metric tensor transforms by a specific scale factor. And the authors actually point out that this concept was introduced to quantum field theory 12 years before their paper, initially sparked by scaling ideas in second-order phase transition theory. And this brings us to where it all officially came together, the foundational 1984 BPZ paper itself. It's so important to realize we aren't just talking about some dry, forgotten academic article here. We're literally talking about the foundational blueprint of 2-dimensional interacting field theories. This was the exact moment where the math of infinite conformal symmetry was decisively outlined for the physics world. It was a real game changer.
Section 2. The magic of 2 dimensions.
This brings us to the absolute crucial aha moment of the entire paper. The authors essentially show that the mathematics breaks wide open based entirely on the number of dimensions we're working in. There's this stark, incredible contrast. In multidimensional spaces, meaning any scenario where d is greater than 2, the conformal group is finite dimensional. It just consists of your standard translations, rotations, dilations, and special conformal transformations. And because it's finite, the math proves just too complicated to solve exactly. The main bottleneck is classifying the fields entering the algebra. But get this. Look at what happens in exactly 2 dimensions. When d equals 2, the conformal group becomes infinite dimensional. And counterintuitively, because it's infinite, it actually becomes exactly solvable using analytical transformations. Now, what's really interesting here is how the authors understate this beautifully in their paper. They write, the situation is somewhat better in 2 dimensions. The main reason is that the conformal group is infinite dimensional in this case. It consists of the conformal analytical transformations. Honestly, somewhat better is a massive understatement. What's truly brilliant about how they achieved this is their introduction of complex coordinates. They transform the space coordinates into complex variables, z and z bar. By treating the space this way, the conformal group splits into a direct product, which massively simplifies the entire universe of these equations and allows physicists to use analytical substitutions to solve previously unsolvable problems. Section 3. The stress-energy tensor engine. If you think of this 2D mathematical framework as a vehicle, you can picture the stress-energy tensor as the engine. It's the mathematical engine driving the entire thing forward. Let's quickly step through the key properties the paper outlines. First up, the authors show that the trace of the stress-energy tensor completely vanishes in 2D. Because of this vanishing trace, the tensor ends up having only 2 independent components. Those components then perfectly satisfy the Cauchy-Riemann equations. And finally, because of all that, the fields t and t bar act as analytic functions of single variables. So the absolute key takeaway here is that because the stress-energy tensor is traceless, it guarantees the theory possesses scale symmetry, and it's also invariant with respect to coordinate transformations. Now, the Virasoro algebra commutation relations are almost like a beautiful mathematical artifact. The BPZ paper proves mathematically that the components of the stress-energy tensor represent the generators of the conformal group, and the algebra of these generators is actually the central extension of the Virasoro algebra, which perfectly coincides with the exact Virasoro algebra. And nestled right within that Virasoro algebra is a vital parameter, the central charge, represented by the letter C. Now, you might be wondering, what's the big deal with C? Well, it's not just a random letter dropped into a math equation. The authors state very clearly that C is the fundamental parameter defining the critical exponents of the theory. It quite literally determines the underlying properties of the physical system you're trying to describe.
Section 4. Families of quantum fields.
Okay, let's dive into this next part. This is where we see how these mathematical components actually interact to build the quantum world. The paper organizes quantum fields into a brilliant hierarchy. I actually like to think of it as a family tree. Step 1, you identify the primary field. In our family tree analogy, think of this as the ancestor. Step 2, you apply linear differential operators to this primary field. Step 3, by doing so, you generate infinitely many secondary fields, which are basically the descendants. The text notes that under conformal transformations, every member of each conformal family transforms in terms of representatives of that exact same conformal family. It's amazing how neatly this architectural blueprint is mathematically expressed in the source material. The dimensions of these secondary fields form an integer-spaced series. You're simply adding a value k to the dimension of the primary field. This simple series acts as the structural foundation for the entire operator algebra.
So why is this family structure so powerful? Well, the text explains that, based on the operator algebra hypothesis, literally any state can be generated by the linear action of these operators. Because of the strict requirement of associativity in this algebra, all that complex information about the secondary fields is neatly accumulated right back into the correlators of the primary ancestor field. Furthermore, the structure constants of this algebra satisfy what the authors call the bootstrap equations. And in certain specific cases, degenerate representations satisfy special linear differential equations, like the hypergeometric equation, which makes these infinite fields wonderfully exactly solvable.
Section 5, Strings and Phase Transitions. Let's zoom out for a second. How is this beautiful, highly abstract 2D mathematical toolbox actually used to solve real-world physical phenomena? Well, the text explicitly names dual applications for this math, and this brilliantly illustrates how the abstract concepts we just spent time learning about bridge two massive, incredibly diverse areas of physics. Let's connect the dots here. On one hand, you have the 2D Ising model. The paper explains that this minimal conformal quantum field theory describes second-order phase transitions in discrete spin systems. We're talking about things like observing the critical point of a boiling liquid or a freezing magnet. This happens specifically when that central charge C we talked about earlier equals exactly 1/2. On the other hand, you have string theory. From a mathematical point of view, dual models are special kinds of two-dimensional conformal quantum field theory. The quantum fields describe the degrees of freedom associated with the string, and conformal symmetry manifests as the reparameterization invariance of the world surface swept out by the string as it moves through space. The dual amplitudes are then expressed in terms of correlation functions of vertex operators, just like in the Venziano model mentioned in the text. So think about that for a second. Whether a physicist is tracking a boiling phase transition or mapping out fundamental strings, they are using the exact same infinite 2D mathematical blueprint from this very paper. Which brings us to the end of our explainer. And honestly, it leaves me with a thought I just can't shake. If the mathematics of a boiling pot of water and the fundamental strings vibrating at the core of our existence share the exact same infinite dimensional symmetries in exactly 2 dimensions, well, how much more of our universe's seemingly chaotic behavior is secretly governed by elegant, infinite symmetries, just waiting to be mathematically uncovered? It's a pretty fascinating thought to leave you with. Thanks for joining me today, and keep exploring.